So this is the session of the module 5b, that is session 3, that is related to the masonry buildings are concerned. So in this today's sessions, we will going to see about the elastic properties of the masonry structures. So as far as the elastic properties of the masonries are concerned, so it's very difficult to determine the properties based on the whatever the constituent materials like masonry units or masonries, mortars, or a grout and a reinforcement. The prediction of the behavior of the masonry assembles on the basis of its constituent material is too complex. Hence, the strength and elastic properties of the integral materials are determined by making the wall specimens and testing under vertical and cylinder the cyclic lateral loading. The first one is the compressive strength, the combined axial and flexure compressive stresses, then tensile stresses, then lastly the shear stresses. We will see it one by one. So now the first one is the compressive strength is concerned. So this compressive strength plays an important role in the load bearing structures, and the compressive strength of the masonry is oftenly used on the basis of the assigning the design stresses, and in some cases as a quality control measure. It's a important is to realize in the relations to other strength characteristics. The basic compressive strength of the masonry, which we can say that the FM shall be determined by the first one, the unit strength of method, and second one is the prism test method. The unit strength method eliminates the expenses of the prism test, but is more conservative than the prism test method is concerned. So now let us see about the unit strength method is concerned. So basic compressive strength of the masonry shall be of the 4 times the basic compressive stress, which based on the strength of units and type of the mortar. Then the unit strength method is based on the compressive strength of the masonry unit and masonry type, and is developed by using the prism test data. Now as far as the prism strength method is concerned, so basic compressive strength of the masonry shall be determined by the prism test on the masonry made from the masonry unit mortar to be actually used in a particular job. So this is the uniform method of testing masonry to determine its compressive strength, and used as an alternative to the unit strength method is concerned. So here the figure which is shows that how this prism test under the axial compressive and as well as the state of the stress units and the motor is concerned. And lastly how this combined the whatever the stress strain relations of the various materials and prisms are concerned. So all this figure itself will shows that how this individual materials and the combined unit, how it will going to be acted under the stress strain relationship is concerned. Now as far as the permissible stresses are concerned, so here permissible compressive stresses in masonry shall be based on the values of basic compressive stress, that is the FV, which is based on the two approaches. The first one is when the prism is not tested, and when the prism is tested. Now let us see about that prism is not tested or unit strength method. In general we can say the whatever the values of basic compressive stresses which are based on the crushing strength of the masonry unit and the grades of mortar, and holds good for the values of the SR not exceeding the 6 and 0 eccentricity, and the masonry unit having the height to width ratio is around 0.75 or less. Now as far as the prism the test is concerned, the basic compressive strength can be obtained by multiplying the specific compressive strength obtained from the prism test with a factor of 0.5. Now the permissible compressive strength is the masonry in the based on the values of the basic compressive stress CFB, multiplying the value by a factor known as stress reduction factor. So the whatever the area of the reduction factor and the shape modification factor. See the combined the whatever the permissible the axial compression and flexure shall be designed to satisfy the equation, that is FA divided by FA, whatever small FA divided by capital FA plus FB divided by small capital FB, so which is less than or is equal to 1. So whereas F small FA is nothing but the calculated compressive strength due to the axial load only, whereas small FB is calculated compressive stress due to the flexure only, and this capital FA whatever it is there, so it is allowable axial compressive stress, and capital FB is a allowable flexure strength which is around 1.2 times of the FA, that is allowable axial compressive stress is concerned. The whatever the unity equation assumes a straight line interactions between the axial and the flexure compressive stress for unreinforced masonry section. So this is a simple portioning of the available the whatever the allowable
Updates
stresses
have been
between
applied.
the axial and the flexure rods, which can be extended for an axial bending by using the bending stress, the quotations for the both axes. So in the interaction formula, the secondary effect of the moment magnification for the flexure term due to axial load is not included, which is an error on unsafe side. However, this error for practical size of a wall will be relatively small, and large overall the factor of safety is around 4, is to adequate to account for this amplifications of flexure term. The code allows the 25% increase in allowable axial compressive stress if it is due to flexure. The permissible flexure compressive strength can be expressed as the function of the masonry prisms strength, like the whatever FP is there, so it is around 1.5 times of 2.5 times of FA. So now the permissible tensile stress is concerned. Now, as a general rule, the design of masonry shall be based on assumptions that masonry is not capable of taking any tension. However, in case of lateral loads, the normal to the plane of the wall, which cause flexure tensile stresses, as far as a example, it is a panel or a curtain portion and the freestanding wall. Then the flexure tensile stresses may be permitted in the design for the masonry. For example, the grade M1 or the better mortar is concerned, so it is around 0.07 times of MPa for bending in the vertical direction, where the tension is developed normal to the bed joint is concerned. Now next is 0.14 times of MPa for the bending in the longitudinal direction, where the tension is developed is parallel to the bed joints, provided crushing strength of the masonry is not less than 10 MPa. Now let us take about the grade of M2 mortar is concerned. Now it is 0.05 times of MPa for bending in the vertical directions, where tension is developed is normal to the bed joint, and it is 0.1 times of MPa for bending in the longitudinal directions, where tension is developed parallel to the bed joint, provided the crushing strength of the masonry unit is not less than 7.5 MPa. Now here the whatever the Here the important thing is that no tensile stress is permitted in the masonry in case of water retaining structures in view of water in contact with masonry. Also, no tensile stress is permitted in earthen retaining structures in view of the possibility of presence of water on the back of such walls is the concern. Now, as far as the permissible shear stress, if you talk, then in a plane permissible shear stress shall not exceed the three conditions, that is either zero point 0.5 MPa or zero point 0.1 plus zero point 0.2 times of FDA, or it will be a 0.12 times of FM square root of FM is concerned, where here FD is nothing but compressive stress due to the dead load, which is expressed in MPa. The whatever the unreinforced machineries in shear fail is any one of the following modes are concerned. The first one is diagonal tension cracking of masonry, generally observed when the masonry is weak and mortar is strong. And second one is sliding of masonry units along the horizontal bed joint, especially when the masonry is lightly loaded on in a vertical direction. And third one is stepped cracks running through the alternative head and bed joints, usually observed in case of strong units and weak mortars are concerned. Now, the permissible shear stresses for the unreinforced masonry is based on a experimental research for the various failure modes. At low pre-compression, that is less than 0.2 MPa, for a sliding type of failure mode, a Morse Coulomb type of failure theory may be more appropriate, and the shear capacity is increases due to the increase in the vertical load. The coefficient of friction here is 0.2 and has been taken used for the masonry codes. However, the recent whatever the research indicate that higher values, that is 0.45 or about, so is a more appropriate, and at the larger pre-compression, that is greater than 2 MPa, tensile cracking of masonry is more likely, which are expressed in terms of square root of the compressive strength of the masonry is concerned. Now, next, this one is the wall thickness, that is cross section and the dimensions are concerned. Now, walls and columns subjected to vertical loads. The wall and columns bearing vertical loads shall be designed on the basis of permissible compressive stresses. Whatever the design involved in determining the thicknesses in case of walls and the section in case of the wall column is a relation to the strength of masonry unit and grade of mortar to be used, taking into consideration various factors such as slenderness ratio, eccentricity, area of section, workmanship, quality of supervision will taken into consideration. Now, as far as the solid walls are concerned, so here thickness used for the design calculations shall be the actual thickness of the masonry completed as a sum of the average of dimensions of masonry unit specified in the relevant standard together with the specified joint thickness. In masonry with racked joint, the thickness shall be reduced by the depth of the racking of the joint for the plastering or pointing. Now, the brickwork is generally finished by either pointing or the plastering, with that in a view that it is necessary to rake the joint while the mortar is green. In case of the plaster work, is racking is intended to provide a key for bonding the plaster with the background. Strictly speaking, the thickness of the masonry for the purpose of the design in case of the actual thickness, less depth of racking. However, in case of design of masonry based permissible tensile stress, for example, design of freestanding wall, if the walls are plastered over, then the plaster of normal thickness is around 12 to 15 mm with the mortar of same grade as used for the masonry, or M2 grade, whichever is the stronger. If the walls are the flush pointed with the mortar of M1 grade or a stronger, then racking thickness can be ignored. So this is all about the masonry elastic properties, as well as the how this the thickness of the section are to be considered.